Every single year, more than 3 million hand grenades are produced worldwide. Each one goes through dozens of meticulously controlled stages, from melting raw metal to the precision dosing of explosives, where the margin of error is less than 1/1000th of a gram. There is no forgiveness in this process. Temperature, pressure, and humidity must remain in absolute control. But what really happens behind the walls of classified workshops? How is ordinary metal transformed into one of the deadliest tools of war, designed with mathematically precise destruction? Stay until the end, and you'll uncover technologies so advanced that even engineers at NASA watch them with unease. Despite the extreme dangers and secrecy, every single step of grenade production is conducted under specialized conditions with cutting-edge technology, ensuring both the safety of workers and the flawless quality of the final product. Grenade production begins with carefully selected components, each with an exact role. Although the recipes for explosive substances like trinitrotoluene TNT, pentarethritol tetranitrate PNE, or RDX remain closely guarded secrets due to their volatility, we know these compounds are derived from chemical reagents that undergo multiple phases of purification and stabilization. The slightest deviation during their creation, an error in temperature or pressure, can trigger a catastrophic accident. Meanwhile, the grenade's body begins as raw metal blanks. They are cleaned, heated, and when necessary, combined with alloying additives to achieve just the right hardness and toughness. The critical step is shaping the shell. This is done either by high-pressure die casting or cold stamping. In die casting, molten metal is forced into massive steel molds under pressures up to 20,000 psi. These molds are designed with millimeter precision, already accounting for every groove, relief, and cavity required to seat the fuse and charge. Alternatively, cold stamping uses 30,000 psi of mechanical force to compress sheets or bars of metal into capsules with walls barely 1/10 of an inch thick, but reinforced in vital zones. What truly defines the grenade's lethality is the surface treatment. After milling and grinding, the body is etched with a relief texture, scored lines, or a cross-hatched grid, often paired with internal concentric grooves. This ensures that when the grenade explodes, it fractures into hundreds of razor-sharp fragments between 1/16 and 1/8 of an inch across. Each shard is engineered to maximize destruction within a lethal radius of up to 50 feet. To prevent premature deterioration, the shell undergoes heat treatment for toughness, then galvanization or painting for corrosion resistance. Automated production lines monitor every stage, measuring wall thickness and groove depth with precision sensors. At the heart of the grenade lies its explosive charge. The filling process is automated and monitored by surveillance cameras, with workers controlling the process remotely for safety. Explosives are measured in granular or powdered form with an accuracy down to fractions of a gram. Surrounding this charge is the initiation system, a fuse and detonator designed to ignite either instantly when the safety lever is released or after a timed delay mid-flight. Modern assembly is as precise as surgery. Tiny components are fitted together with accuracy down to 1/1000th of an inch. Unauthorized access is strictly forbidden. Once assembled, grenades undergo multi-stage testing, checking seals, detonation speed, and fragment uniformity. Advanced X-ray scanners examine internal structures, while artificial intelligence systems simulate impact conditions. What seems like a simple battlefield weapon is in fact a masterpiece of metallurgy, chemistry, mechanics, and electronics, all balanced in pursuit of reliability. The final product is devastating yet compact, typically no more than 5 inches long and 3 inches in diameter, packing the explosive force of half a pound of TNT. Soldiers rely on this combination of portability and raw destructive power in the most extreme situations. Over the past 2 decades, grenade technology has evolved dramatically. Modern insensitive munitions are designed to resist accidental detonation caused by impacts or temperature extremes. These innovations have reduced accidents by more than 70%, with over half of new contracts in Western militaries now requiring these safer designs. Usage is staggering. During intense military conflicts, armies can consume thousands of grenades per day, while global training exercises and testing account for up to 3 million units annually. In some years, over 60% of production is exported. But this story of transformation doesn't stop with weapons. Every year, over 9 million tons of copper scrap are recycled, enough to build 1,800 statues of liberty. Where does this scrap go, and how is it reborn into something essential for modern life? The process begins at recycling plants where cables, transformers, and wires arrive by the ton. After careful sorting, shredding, and density-based separation, the copper is purified through melting and electrolytic refining, achieving 99.9% purity. This refined copper is cast into ingots, then drawn into wires thinner than a strand of hair. These wires, insulated and bundled, become the veins of our electrical world, transmitting energy to homes, factories, and skyscrapers. The cycle is endless. Copper can be recycled infinitely, without losing quality, saving 85% more energy compared to mining fresh ore, and reducing carbon emissions by 65%. In fact, 1 million pounds of recycled copper saves enough energy to power 1,000 homes for an entire year. From scrap that once seemed worthless emerges the foundation of global infrastructure, and copper's story intertwines with another engineering marvel, the electric motor. Over 300 million motors are manufactured annually, from tiny fans to massive engines that power industrial machinery. Inside each motor lies a world of precision: the stator, rotor, windings, bearings, and cooling systems, all crafted with meticulous care. Stator windings are laid loop by loop, like threads in a loom, while rotors are balanced with the accuracy of jewelry. A single mistake, a misaligned coil, an unbalanced shaft, can cause catastrophic failure. Before leaving the factory, every motor is varnished, baked, balanced, and tested under load. The result is a machine capable of running thousands of hours without rest, converting electrical energy into the mechanical force that drives the modern world. From grenades engineered for battle, to copper reborn from scrap, to motors powering civilization, these processes reveal the hidden symphony of science, precision, and human ingenuity. Each step, whether in weaponry, recycling, or industry, reflects a common thread: the relentless pursuit of efficiency, safety, and perfection in design. Imagine thousands of glass threads, each thinner than a human hair, flowing together like rivers, converging into one massive current. These threads are transformed into a material so strong it rivals steel, yet so light it defies expectations. This is not science fiction, it's the creation of fiberglass rebar, a revolutionary building material, reshaping the future of construction. Every year, billions are spent battling rust, repairing bridges, and parking garages destroyed by corrosion. But here's the twist: fiberglass rebar doesn't rust. It's twice as strong as steel, 4 times lighter, and resistant to the very elements that eat away at traditional metal. The global demand for this innovation is growing rapidly, and today we'll unravel its journey from fragile glass strands to a mighty force in modern engineering. At the start of this process stands an enormous structure called a creel, resembling a vast library of threads. Hundreds, sometimes thousands of giant bobbins are mounted in perfect rows, each holding delicate roving made of fiberglass. Unlike window glass, this fiberglass is crafted by melting glass and drawing it through microscopic holes, producing strands with incredible tensile strength. These countless threads stretch forward, merging into a thick, fluffy bundle, a dry white river that will soon become the backbone of fiberglass rebar. Before transformation, precision is key. The bundle passes through guides and tensioning devices to ensure every single thread is aligned with perfect balance. If one strand is too loose or another too tight, the entire structure could weaken. Once aligned, the river of glass enters a critical stage: immersion in resin. Thick, sticky polymer resin, made from polyester, vinyl ester, or epoxy, coats every fiber. Additives enhance its powers: pigments for color, UV inhibitors for sunlight resistance, and flame retardants for fire protection. This resin bath is no less than a baptism, soaking every fiber to prepare it for strength. Next comes the forming die, the very heart of the process. Picture a steel plate with a perfectly polished hole, heated precisely to transform the resin-soaked bundle into shape. As the bundle passes through, excess resin is squeezed out, the fibers compress tightly, and the heat sparks polymerization, turning liquid resin into solid form. Emerging from the die, the rod takes shape but remains soft. To give it grip inside concrete, spiral windings of resin-soaked threads are wrapped around its surface, and sometimes quartz sand is sprinkled on while still sticky, ensuring the rod locks firmly into any concrete structure. From here, the rebar journeys through a long curing tunnel, a furnace heated to nearly 400 degrees Fahrenheit. This is where magic turns into permanence. Molecules link into a rigid 3-dimensional network, baking the rod into stone-like hardness. Finally, a pulling device with caterpillar-like grips draws the rod forward at a precise pace. The endless ribbon of fiberglass rebar emerges strong, light, and corrosion-proof. The World Gold Council stands as the global voice for the gold mining industry, guiding companies toward responsible, safe, and sustainable practices. Their mission goes far beyond profit. It's about ensuring gold is mined in a way that protects the environment, benefits local communities, and adheres to the highest international standards. Through rigorous research and detailed market analysis, the WGC empowers investors, governments, and industry leaders with the information they need to make smart, ethical decisions. Gold mining today is a highly complex process, starting with determining the gold reserves in a site and ending with bars or coins ready for market. Before a single ounce is extracted, member companies perform extensive geological surveys, exploratory drilling, magnetic field measurements, and soil analysis to map out exactly what lies beneath the surface. Environmental impact assessments are conducted to safeguard ecosystems and public health, and legal permits are obtained before operations begin. There are two primary methods of mining: open pit and underground. Open pit mining is used when the gold ore lies near the surface. Layers of rock and soil are removed to expose the gold-bearing ore. Underground mining, on the other hand, is reserved for deeper reserves, where networks of tunnels are carved out to access the ore. Once extracted, the ore is crushed and subjected to advanced processing to isolate the gold. The most common method is cyanidation, where gold is dissolved in a cyanide solution and then separated through absorption. Two popular variations, carbon-in-leach (CIL) and carbon-in-pulp (CIP), use carbon particles to capture the gold, allowing it to be separated without losing purity. These processes are strictly monitored under WGC safety and environmental guidelines to ensure that chemicals like cyanide do not damage surrounding ecosystems. Once separated, the crude gold heads to the smelter. Through high-temperature heating, impurities like silver and copper are removed. Refining, whether through electrolytic or chemical methods, pushes purity to 99.5% or higher. The result is pristine gold, ready to be cast into bars or coins, carefully packaged and shipped to banks, jewelers, and investors around the globe. WGC's commitment doesn't end at mining and refining. Member companies must regularly monitor air, water, and soil quality in surrounding areas, ensuring no pollution harms local communities. They are encouraged to invest in infrastructure, education, and healthcare projects, creating jobs and raising living standards. On a global scale, the Planet Gold Guyana initiative is tackling one of gold mining's most dangerous practices: the use of mercury. Mercury is a potent neurotoxin, contaminating water, soil, and air, and posing severe risks to human health and wildlife. To eliminate this threat, Planet Gold Guyana is introducing innovative, mercury-free technologies like the Gold Catcha, Gold Cube, and Blue Bowl. The Gold Catcha is a portable gravity concentrator designed to separate gold without chemicals. It uses water flow and vibration to let heavy gold particles settle while lighter material is washed away. Simple to use, low cost, and efficient for alluvial deposits, it offers high recovery rates, though it's less effective with ultrafine particles. The Gold Cube takes a different approach, using layered concentration plates to trap gold as water and sediment flow over them. Pre-screened ore under 1 mm passes through multiple stages, with gold settling onto the plates while lighter debris is washed out. The final product is clean, high-purity gold without a drop of mercury. Both methods represent a safer, more sustainable future for artisanal and small-scale gold mining, ensuring miners can work profitably without compromising their health or the planet's well-being. From cutting-edge industrial mines to small artisanal operations, the message is clear: gold can and must be mined responsibly. The World Gold Council and initiatives like Planet Gold Guyana are proving that when innovation, regulation, and ethics work hand in hand, we can extract one of the world's most prized resources without sacrificing the environment or human health. This device stands out as one of the most efficient tools for separating gold from various ores, capable of isolating even the smallest gold particles with remarkable precision. However, its primary drawback is a higher investment cost compared to the Gold Catcha. The third device worth noting is the Blue Bowl. This disc-type gold separator utilizes a vortex of water to concentrate and recover gold. It's a simple yet highly effective device, ideal for separating pure gold from alluvial sand, especially when dealing with extremely fine particles. To use it effectively, the ore must be finely ground and large impurities removed. The raw material is placed into the blue bowl, and the water flow is adjusted to create a gentle vortex. This swirling motion encourages heavy gold particles to settle at the bottom, while lighter sand is swept away. The gold kacha, gold cube, and blue bowl together provide miners with the tools to recover gold efficiently from alluvial sources without damaging the environment or risking human health. Planet Gold Guyana supports small-scale miners in adopting these mercury-free methods, ensuring economic viability, safety, and long-term sustainability. In East Africa, the African Gold Refinery (AGR) in Uganda stands as one of the region's largest gold refineries. AGR manages the process from raw material procurement to the final market-ready product. Raw gold, whether in the form of ore or gold dust with low purity, is first tested extensively before processing. The gold is heated in a furnace at extremely high temperatures until it liquefies.